Hello and welcome to our third and final day of section 2.7, derivatives and rate of change. Today we're going to be focusing on the rate of change piece, which in turn is velocity. So we're going to be looking at velocities. Average velocity. We talked about how it's displacement over time or distance over time. And one equation that you can use to find it is f of a plus h minus f of a all over h. The one that we used was f of b minus f of a all over b minus a, our old school slope, our average slope. Okay. But in order to find instantaneous, we talked about how you take this function and you go ahead and add on the limit as h approaches 0. Okay. So we're going to be looking at average and instantaneous velocity today. So if a rocket is launched with an initial velocity of 196 meters per second, its height in meters after t seconds is given by capital H of t. It gives the equation here. Some things I want you guys just to take notice of. We have it says initial velocity of 196 meters per second. That can be found in our equation right here. Okay, velocity is typically the number that's right in front of the variable that's by itself. The number that is in front of whatever is squared, that's usually, if it's a quadratic, representing gravity. The reason it's usually negative, or it is negative, is because gravity pulls you down. So that is our equation that represents the launch of our rocket. Okay, so we want to find, using a limit, find the velocity function for the rocket. So in order to find velocity, okay, that is this instantaneous velocity, this is this guy. We're going to use this equation. One thing to also take note of is this is also what we used yesterday, or in our last lesson, to find the derivative of a. So derivative and an instantaneous velocity are the same thing. Okay, so velocity is really equal to the derivative of capital H of t. And our limit equation is our limit as little h approaches 0 of capital H. And over here we have a plus h. That's a derivative at a, but we are finding it at t. So it would be t plus h minus h of t all over little h. Okay. I am going to go ahead and do a little work, little side note, to find capital H of t plus h. Okay. And I know kind of the t's and plus signs get confusing, so I always try and like curve my t a little bit to help. But when I plug it in, I would have 196 parentheses t plus h minus 4.9 times t plus h squared. Okay, now from here, I would distribute my 196. And I need to distribute my negative 4.9 to t plus h when I FOIL it. And when I do FOIL this, I would have t squared plus, I would have th plus th, so plus 2 th, and then plus h times h, so h squared. So I'm going to distribute negative 4.9 to that. So I'd have negative 4.9 t squared, and then 4.9 times 2 is negative 9.8 th, and then minus 4.9 h squared. Then I would just check if I can combine any like terms here, and I cannot. So I'm just going to go ahead and plug it into my velocity equation. Okay, I'm just going to save some room, erase this because I'm probably going to need the space. Now we have our limit as h approaches 0. Capital H of t plus h, that's everything I have here, so I'm just going to rewrite this down. So I have 196t plus 196h minus 4.9 t squared minus 9.8 th minus 4.9 h squared. Then I'm going to subtract h of t, which I have listed just above here. So it's going to get crowded. So I got 196t minus 4.9 t squared. All of that over h. Then I would distribute my negative, so I'm just going to write it above. I'd have 196t, and if I take negative times negative, I have plus 4.9 t squared. And when I look at this, I would see that my 196 t's, they will cancel, and my t squareds, my 4.9 t squareds, those will also cancel. Okay, and what I have left, everything has an h, so I'm going to go ahead and factor out my h. So I have 196 minus 9.8t minus 4.9h all over h. Those h's will cancel. And now, since I've canceled out that h, I can plug in 0 for h. And what I am left with is 196 minus 9.8. It's minus 9.8t. This is our equation to represent our velocity, which is also our derivative of h of t. So there's our velocity equation. Okay, so that is our answer for part A. Part B says find the velocity at 3 seconds. Well, the good news is in part A, we just found our velocity, our v of t, was 196 minus 9.8t, I do believe, if I go back. Yeah, that should be right. Okay, so in this case, in order to find this, I know what t is. T is equal to 3 seconds. So I'm going to go ahead and plug in 3 for t. And when I do that, I will type this into my calculator and I will get 166 point, I do believe it's 6 repeating. Let's see. Maybe not. Yep, 166.6, and it's velocity. And velocity in this case is measured meters per second. So that's our velocity at 3 seconds. Part C. At what time will the rocket return and hit the ground? If I want to know when something hits the ground, I am talking to you about the position of the object. And if I'm ever referring to a position, I'm always referring to the original equation. Okay, so that is function h of t. Okay, what do you guys know about things when they hit the ground? What is the height of an object when it hits the ground? The height is equal to 0. I'm not sure why that just switched. All right, so that is our height is equal to 0. I'm saying this is function h of t, and we know our height when I hit the ground is equal to 0. So I'm going to go ahead and plug in 0 for right here. So I'm plugging in 0, and do you guys see how it says at what time? So I'm solving for t. Then from here, I see it's a quadratic, but I can actually factor out a greatest common factor of t. So I'd have 196 minus 4.9t. Then I would go ahead and set each part equal to 0. This one's already solved, so at 0 seconds I'm on the ground, which makes sense because I probably haven't left yet. And then if I solve this one, I would go ahead and I'm going to add 4.9 to the other side, 4.9t. And then if I divide, I should get t is equal to 40 seconds. So at what time will the rocket return and hit the ground? This is our only valid option, but it is always important to make sure you include that you found t equals 0 as well. Okay, that is part C. Part D then says, with what velocity does the rocket hit the ground? Well, we know our velocity equation, v of t, from part A is 196 minus 9.8t. And then with what velocity? Well, what we need to know is the time. We just found in part C the time we hit the ground was 40 seconds. So what I need to do is find v of 40. And if I type all of that in, I will get negative 196 would be my answer. And then this would mean meters per second. And it is okay to have a negative velocity. All it is telling us is the direction, which makes sense because I'm on my way down, so my velocity should be negative. Okay, so it's telling me we're moving downward. That is part D. Okay, so that is our first example. Now we're going to move on to graphing derivatives. Okay, this is something that doesn't always come naturally to you. Don't get discouraged. It will get better with time. We will do more practice with it. But we are going to graph derivatives. Okay. One thing I want you guys to always remember is your original function is your position. So that is your f of x function. And then your velocity is always your derivative. Okay. Well, we talked about what derivatives are in our last lesson. Derivatives are your slope. Okay, so if I am asked to draw the graph of the velocity function, I am asked to graph the slopes of my original, which seems a bit bizarre, but we can totally do this. Okay. The first example is nice because these are all nice slopes that you guys can all find. Okay. So my first one, slope, I remember rise over run. Okay, so I'm going up 3 and over 1. So my slope at this point from 0 to 1, my x values are 0 to 1, my slope is equal to 3. Okay, so I'm going to go ahead from 0 to 1, and I'm just going to say it's always a slope of 3, so I have this nice constant line here of 3. Just going to make a little note to myself. Slope equals 3, and that's why it's there. Okay. My next little set of slope from 1 to 2, this is a slope of 0. So I go ahead and I plot when my slope is 0. Okay. Moving on to my next one, we're going from 2 to 3. This is a negative slope. I'm going down 2 over 1. So my slope here is a negative 2. So I'm going to have to extend my little bar here because I need to go down to negative 2. So I have negative 1, negative 2. And from here, from 2 to 3, how my x values, I have a slope of negative 2. Then I look from 3 to 4. Those are kind of our favorites. We have slopes of 0. From 3 to 4, I have a slope of 0. And then from 4 to 6, it's saying all the same constant slopes. So I'm just going to count it up. My rise over my run, I'm going up 2 over 2. So my slope is equal to 1. So from 4 to 6, it's going to be 1. So if I ask you to graph the velocity or the derivative, I'm asking you guys to graph slopes of the original function. Okay. So there is example 2. Example 3, okay, it's giving us a bunch of information, and we need to decipher what this information looks like, and then we need to sketch the graph. Okay, so for my first one, we need to sketch the graph of g, for which g of 0 equals g prime of 0 equals 0. Okay, well, let's start with the easy piece. We know that g of 0 equals 0. What that is telling us is I have a point, right? It's my original function. It's talking about my position. I have a point at 0, 0. So I know I have the point from these two pieces of information. 0, 0. And I plug in 0, I get out 0. So I'm just going to mark that right on here. Okay. Now I'm going to go ahead, and what does the next piece mean? My derivative at 0 is 0. Okay. So when I put these two things together, they tell me that my slope at x equals 0 is 0. Okay. The next piece of information, I'm just going to write down what the rest of them here mean. We got g prime of negative 1 equals negative 1. So when it's talking about g prime, I know it's talking about slope. So my slope at x equals negative 1 is negative 1. This piece, g prime of 1 equals 3, tells me my slope at x equals 1 is 3. And then lastly, my slope, because So it's derivative, g prime of 2 at x equals 2 is 1. Okay, so when I graph slopes, these are not going to be nice linear lines like this last one. There's going to be some curves to it. Okay, when I graph slopes, I use 45 degrees as kind of like my reminder what I have going on. If I have a straight 45 degree, if I go through a crosshair here at 45 degrees, this is telling me I have a slope of 1. Okay. If I go ahead and I draw something steeper, I know I have a slope bigger than 1. Okay, so if I ever go higher than that 45 up here, that means I have a number bigger than 1. And then the opposite, if I go below that line, this direction, this means I have a slope that's less than 1. Okay, so some things to keep in mind as I go through this. Same thing applies to negatives. I always think about -1 slope kind of going at that -45 degree angle. Okay, so let's start with the first one. We know our slope at 0 is 0. So to be a slope of 0, I could have a straight linear line like this. The other thing I could do, we're talking about the tangent line, is I could have a little curve like so. Okay, because if I think about my tangent line, touches at just one point, my tangent line would have a slope of 0 here. Okay. Then let's go on. Do I know what I have at 1? I'm just going to go in numeric order. We got to go into 1. At 1, I need to have a slope of 3. Okay, so if this is my slope of 1, in order to have a slope of 3, I'd have to be rising more steeply than a 45. So as I cross through 1, I would say that's a pretty good, nice steep line. So it would have a slope of 3. Then I'm going to 2. At 2, I have to have a slope of 1. So in order to have a slope of 1, I kind of want to cross through 2 at a 45 degree angle. So I might kind of turn, go like this. I would have that value. Okay. I got 1, 2, 3. Do I know what is going on at 3? I do not. So I'm just going to continue this on here. Could go on and I'm not sure how it ends. And then the only last piece is I got to do at -1. At -1, I have a slope of -1. Okay, so I want to cross through in order to have a slope of -1. Have to look like this. So I'm going to cross through here with a negative. Okay, so this one would be one option that satisfies this criteria. Let's just confirm, as you should, as you guys take a test, that everything works out. I have the point 0, 0, excuse me, right here. Then I have a slope of 0 at 0. It's a slope of my tangent line. So at 0, if I draw my tangent line, I should see that that's a straight line that's constant, horizontal, and it will have a slope of 0. If I go to, I'm just going to go to -1. Does it look like I have a slope of -1 here? Yes. G of 1. So at 1, I have a slope of 3. Does it look like I have a steeper slope than just 1? Yes. So I would say it looks close to 3. And then G prime of 2 equals 1. So at 2, does it look like a slope of 1? I would say yes, it does. Looks like it's crossing at that 45 degree angle. Okay. So that is it for example 3. You have some of these on your homework, you guys. Just give them your best try, and we can work through them together more when we need to, but just give them a good try on your own first. Okay. Otherwise, that is it for today's notes. Most of it is pretty straightforward. Some of it actually goes back to what we did in our last lesson, finding the equation of a tangent line. I do want to look through 31 through 35 odd just a little bit. I don't want to give it away too much, but on 31 through 35, it says each limit represents the derivative of some function f at some number a. State such an f and a in each case. Okay, so we got to go back to our limit equations and use those to help us out. And let's see, I'm not going to be able to write on this. All right, so there's 31, 33, and 35. So what we need to go ahead and use is our equations for the derivative, okay, and then come up with f and a. So we have our limit, one derivative, as h approaches 0 of f of a plus h minus f of a all over h. That is the derivative at a. Okay, so what they want us to come up with is what is the function and what is the value of a. Our other derivative equation that we had was our limit as x approaches a of f of x minus f of a all over x minus a. Okay, so we need to look at all three of these and decide which equation are they using. I would say, since it's going to h equals 0 for these two, I would be comparing them to this definition of derivative. And this one is going to a number 5, so I'm comparing it to this definition of a derivative. Okay, and so what you would do, for example, for part A, for number 31, is you'd say, well, what is my function that they're talking about? What am I plugging it into? Well, my a plus h, that actually, it gives me away what a is. It's 1 plus h, so my a is the number 1. Okay, and then what function would you be plugging 1 plus h into? It'd be x to the 10th. So that would be your answer for 31. And you could just check if I found f of a, if I found f of 1, if I plug 1 to the 10th in, is it 1? Yes. Okay, so that's how you handle number 31. 33 is actually, I think, a little bit more straightforward because we need to find f of x and I need to find a. F of x is what's listed right here. Who is in the same spot as that? 2x. So f of x is equal to 2x. And then a, you can either find it here or I can find it here. So a is the number 5. Okay, so you use those to compare. I'll let you guys try and work through 35 on your own. But those are the definitions that they're using to kind of figure out who is function f and who is the value of a. Okay. If you have any other questions, feel free to message me. Otherwise, have a great day and I will see you later.